Trains today is more than a means of transportation. They are technological marvels racing through space and time. And behind every high performance train lies a traction motor, quietly doing the heavy lifting. A traction motor is the device that converts electrical power into the mechanical force that drives the wheels of a train. It needs to be robust, efficient, and capable of delivering torque across a wide range of speed. From the aerodynamic Shinkansen of Japan to the elegant Eurostar zipping under the English Channel, these motors are the heart of electric propulsion. Hello, welcome to Surge Pulse. Today we will learn about the vector control method of induction motor for speed control in locomotives. So, let's get going. In the past, DC motors were the dominant choice for traction application because of their excellent torque speed characteristic and ease of control. But as railway networks demanded higher reliability, reduced maintenance, and better energy efficiency, the shift to AC motors, especially the three-phase squirrel cage induction motor, became inevitable. These motors are rugged, simple, and efficient. Modern high-speed trains like the TGV in France and Talgo's Avril in Spain use AC traction motors to meet the rigorous demands of long-distance, high-acceleration rail travel. Even in India's Vande Bharat, a semi-high-speed train relies on these motors to achieve its sleek 160 km per hour cruising speed. However, having a powerful induction motor is only half the story. Controlling that motor with precision and responsiveness is what truly defines modern electric rail. Speed control of induction motors is more complex than with DC motors due to their nonlinear interdependent flux and torque characteristics. Broadly speaking, speed control methods falls into two categories: scalar control and vector control. Scalar control methods, like the volts per hertz approach, control the magnitude of voltage and frequency to maintain a constant magnetic flux in the motor. They are simple, cost effective, and work reasonably well where dynamic performance is not critical. Earlier electric locomotives and urban transit systems often use scalar control due to its simplicity. But for applications demanding real time responsiveness, such as a Eurostar train climbs a steep gradient or a Shinkansen decelerates rapidly at a station, scalar controls falls short. This is where vector control comes in, also known as field oriented control. Vector control changes the game by decoupling the motor's torque and flux producing components. This allows independent control just like in DC motor and offers far superior performance in terms of torque precision, dynamic response, and low speed behavior. Trains like China's Fuxing Hao and India's Vande Bharat use vector controlled induction motor to optimize both efficiency and control. Let us now understand how vector control works in detail. The core idea is to transform stator current into rotating reference frame using mathematical transformations like Clark and Park transformation. First, in the Clark's transformation, the three-phase components, that is the rotor current of an induction motor, is converted to a two-axis vectors representing the rotor current. These two-axis vectors are not rotor current but represents the same. The rotor current has now been transformed into two-component orthogonal stationary frame. The transformation is done using these equations. Here, clockwise is positive and anticlockwise is negative direction. So, IA points in the alpha direction, IB points in the minus cos 60 of alpha direction, sin 60 of beta direction. IC points in the minus cos 60 of alpha direction, minus sin 60 of beta direction. The Park transformation converts the two component in the alpha beta frame to an orthogonal rotating reference frame, DQ. For this transformation, the signal of position sensors from the induction motor is fed to the control systems, which provide the electrical reference for the mechanical position of the shaft. Implementing these two transformations in the consecutive manner simplifies computation by converting AC current and voltage waveforms into DC signals. This converts the signal from three-phase system of induction motor to two components, the D-axis component, which controls flux, and the Q-axis component, which controls torque. The control system then regulates these components independently using feedback from current and speed sensors. A set of nested control loops, an inner current loop, and the outer speed loop ensures precise tracking of motor commands. The inverter then uses PWM signals to adjust the stator voltages accordingly, keeping the motor operating exactly as desired. This level of precision is what makes vector control so powerful for traction. Not only it does provide smooth acceleration and deceleration, but it also enables regenerative braking, which feeds power back into the grid when the train slows down. Vande Bharat uses this feature extensively in its regenerative braking mode, improving energy efficiency. High-speed systems like TGV and Fuxing also leverage field weakening through vector control to exceed their base speed while keeping currents within safe limits. So next time you see a high-speed train glide across the landscape, remember, underneath that sleek exterior is a symphony of physics and control engineering, where vector control ensures that power is delivered with grace, speed, and precision. If you found this explanation helpful, do not forget to like the video. Leave a comment if you have questions or thoughts, and of course, subscribe for more deep dives into electric transport, control system, and advanced engineering technologies. Your support helps keep this channel on track, literally and figuratively. See you in the next one. Thanks a lot.